Dear student, I welcome you all for this online session of Control System Laboratory, wherein today we will try to simulate typical second order system for various transfer function through addition of pole, deletion of pole, addition of zeros, and various other stability concern that will come into picture for second order system. In today's session, so we will see the objective, apparatus required, procedure, tabular column, demo of the experiments. Since basically this is a simulation based experiment, let me give a brief introduction about how the second order system, what are the various factors that you need to calculate, and then we will move to the Matlab environment wherein we will write the code and we will try to simulate. So coming to the second order system, as we already discussed the basics about second order system in frequency response of a second order system, the second order system transfer function, how we will calculate the characteristic equation, how the roots will be placed in imaginary axis, how to plot pole zeros, and what is the RH criterion. So all these are the prerequisites for this experiment. I hope you can visit any of the prescribed control system test book for more information about second order system, damping ratio, zeta, and for various transfer functions. And in today's simulation based video, what I will be like to present, I have taken a few examples, and I thought of giving what are my views related to how does the second order system behave. So coming to the objective of second order system, the student basically will learn how to program the step response of a second order system, and will have a different transfer function example so that they can evaluate how does the time domain specification that can help the student to learn more about how the general characteristics can behave. So if we input a unit step or any of the input signal, so what is the tool? We required a software tool, that is Matlab or Octave. So let me make it clear. So what are the program or the commands what we use in Matlab and Octave? Octave is a freeware software wherein student can download and can use it. So we prefer students to use freeware softwares to get enough knowledge, and there are little bit hindrances, but most of you can use a freeware software to enrich and can write your own code. So almost the syntax remains same for both Octave and Matlab. So coming to the second order system, so let me take a case study. So as I already explained you about the frequency response experiment, how does the second order system, what are the damping ratio, and what is the steady state error that you need to calculate, and vice versa. So in today's case study 1, so let us simulate for a second order system and determine a step response and evaluate with respect to the time specification of the transfer function. So for that we should know prerequisite knowledge, that is about second order system, how the standard form of transfer functions are represented, and what are poles and zeros. I hope that majority of all my students have already attended around 20 to 25 sessions related to control system. By now I think you can able to identify the poles, zeros, and you can able to predict the stability. And I won't go in detail about all the concepts, so that will be covered in the theory session. So here in particularly in the laboratory session, I will give more emphasis about how to conduct the experiment and how to draw the inference about the values what you obtain while simulating in Octave or Matlab IDE environment. So I hope you are almost known about the standard form of second order system, where is C of s by R of s is given as omega n square whole divided by s square plus 2 delta omega n s plus omega n s square. So the dynamic behavior of a second order system can be described or can be expressed in zeta and omega n. So where zeta and delta both are same, in few of the textbook they have used different nomenclature, but that both the syntaxes are same. So I hope the zeta, if it is from 0 to 1, we call it as complex conjugate, the poles, and they will lie in left half of the S-plane. The system is underdamped, and you can observe the oscillations in the transient response if you give any input signal. When it comes to zeta is equal to 1, the system is critically damped. If it is greater than 1, it is overdamped. If it is 0, the system is undamped and the transient response does not die out. The oscillation keep on continue till infinity. So these are the few prerequisites for case studies. So why I have taken this under procedure, because all this case studies information and standard norms you should know, then only you can able to express and you can able to simulate. So moving on, so what are the time response characteristics that you need to derive from a second order transfer function? So one is rise time. It is defined as the time required for a response for any signal response to rise from 10 to 90% of a full wave underdamped system values. So it is expressed as pi minus tan inverse of root of 1 minus zeta square divided by zeta whole divided by omega n square root of 1 minus zeta square. So this is the expression for rise time. When it comes to settling time, it is defined as a time required for a response to decrease and stay within the specified percentage, that is 2 to 5% of its finish value or a final value. So these are the, for 2% it is 4 tau, which is 4 divided by zeta omega n. If it is a 5%, it is 3 tau, it is 3 divided by zeta omega n. So what is the peak overshoot? When my signal will be maximum? So that is the, how does the system will record its final value? It is e power, it is exponential to the power minus pi zeta root of 1 minus zeta square. So it is quite often it is expressed in terms of percentage. The peak time is the time required to reach the first peak overshoot. So it is expressed as Tp, which is pi divided by omega n square root 1 minus zeta square. So all these equations are derived for a second order system, and you need to calculate theoretically in order to compare the simulated value with the theoretically calculated value to observe how does the system will behave in the virtual environment. So moving on, so this is the program code wherein you can able to simulate for a second order system. So CLC is a clear screen instruction in the Matlab or Octave. So here percentage PRG, that is program with respect to C of t, that is output transfer function. So here if you consider a generalized transfer function which is taken as g of s is equal to 5 divided by s into s plus 1. So for that, or s plus 5, you can take any transfer function. So here I have taken numerator as a 5, denominator as 1, 1, 5. So that is you will get s square plus s plus 5s. So that is the denominator. So what is the prefix? That is value that is embedded to the power that you need to list out in denominator as well as in numerator. So g is the variable wherein the transfer function will be performed. If you write a syntax tf, numerator by denominator, and Kp is the DC gain of the transfer function, because we need to calculate the steady state error, that is zeta for unit step, unit impulse, or any of the input signal that you are providing to the system. So ESS is the steady state error, which is given as 1 divided by 1 plus Kp. So Kp is the, what is the DC gain of the transfer function, numerator by denominator. So omega is calculated as square root of denominator by 3, so that is the third element. So we know that omega n square is 5, so if you want omega n is square root of denominator of third element is 3, so that will be taken and it will be computed for omega. And zeta is denominator 2 divided by 2 into omega, that is the zeta value. So that whatever the value that is specified in the denominator, that is 1 divided by 2 into omega, will get zeta. Similarly, you can calculate the delay time as 1 plus 0.5 into zeta divided by omega. Ts as settling time, 4 divided by zeta into omega. Similarly, Tp is the peak time, pi divided by omega into square root of 1 minus zeta whole square. Rise time, pi minus tan inverse, so it is a syntax called A tan, square root of 1 minus zeta to the power square whole divided by zeta, and again it is divided by omega into square root of 1 minus zeta whole square. So this is the equation that we already come across in the time domain. This is the peak overshoot, which is exponential minus zeta into pi divided by square root of 1 minus zeta whole square into 100. As I told, it will be expressed in percentage. Step function, it will plot for the transfer function g, and you can give the title as step response of c of t, and it will plot in a figure, and it will plot pole versus 0 map also for the transfer function. So it will be title pole 0 map of a c of t. So again it will plot another figure. So if you run this in the Matlab or any of the tool, you will get the results. So what is the procedure? You consider a transfer function g of s as 5 divided by s into s plus 1. If you multiply this, you will get s square plus s plus 1. But I want a closed loop transfer function, so which is c of s by r of s, which is g of s whole divided by 1 plus g of s into h of s. Assume that h of s is 1, unity feedback, so you will get 5 divided by s square plus s plus 5. You compare this with standardized equation, you will get omega n square as 5, zeta will be 1 divided by 2 omega, so that you will get 0.224, and omega n 2.236. So this is how you calculate, and you can write the program code which has been explained previously in GU IDEA environment, or you can use a Matlab to obtain the step response of a curve, and you can evaluate the time domain specification. You can run the program and obtain step response, how it will appear on the screen by using a pointer, or you can go for a characteristics curve. So this is the output, what you can observe if you write the program code for a second order system, so that we can able to simulate now in the Matlab. So wherein you need to calculate the delay time, rise time, peak time, settling time, peak overshoot, so what is the simulated value and the theoretical value what you adopted. So now shall we go for the demo. So this is my Matlab editor toolbox. So I have written the same program lines in the Matlab. So without wasting any time, so let me run this transfer function of what we have defined, 5 divided by s into s plus 1. So if I run the transfer function, so I will get the roots. This is the pole 0 roots what I had obtained. Similarly, I will get a step response of C of t. So before going in detail, so let us see the output. So this is my transfer function, which is, you can observe this is my command window. So 5 divided by s square plus s plus 5, it is a continuously timed transfer function. Kp will be 1. So steady state error will be 0.5 and omega will be 2.2361. And zeta, according to the formula, so we obtain 0.2236. Td will be 0.51, Ts will be 8, TP will be 1.4415, and the rise time is 0.8242. Peak overshoot is 48.63. So if I want to see on the waveform, so this is my step response plot. Here just right click on the screen, select characteristic curve. So this is, if I hold on to the point, I will get a peak overshoot, it is 48.5%, peak amplitude 1.49, and peak time is 1.47. Similarly, if I want settling time, I will get 7.56. If I want rise time, I will get 0.553. So even I can get the steady state, so it will be 1 final value. So whatever the oscillation, so that will go and reach to final value, which is 1. So with this, so let me stop the second order system. Even there are so many case studies are there, so we will have one more session. So thank you.